The Great Pyramid is a mountain of stone misplaced by human hands. How did ancient builders move millions of tons of rock without modern machines? The secret was not just muscle, but a hidden world of organization, the very first global supply chains. By the end of this, you will understand the invisible systems that turned raw stone into immortal monuments. We will uncover how river highways carried obelisks and why a quarry could be more valuable than a gold mine. What does it truly take for a civilization to reshape the world? These monumental structures were the ultimate expression of a civilization's confidence. Across the ancient world, from the sun-baked plains of Mesopotamia to the rugged hills of Greece, eras of explosive construction marked a society's arrival on the world stage. This was the ancient building boom, a phenomenon far more significant than a single temple or palace. It was a declaration. A ziggurate's towering steps proclaimed a city's devotion to its gods. A sprawling Greek temple complex demonstrated a city-state's wealth and civic pride. These projects were the billboards of antiquity, broadcasting messages of divine favor, military might, and economic dominance that everyone, from the local farmer to the visiting ambassador, could not possibly ignore. But this architectural ambition came with an almost unimaginable price tag, not in coin, but in sheer physical material. We must look past the finished glory to see the foundational hunger. A building boom of this scale is an industrial appetite. It consumes resources. Think of it not as art but as metabolism. A civilization decides to build, and suddenly it needs to eat mountains. This relentless, insatiable demand for stone by the millions of tons is what created the central problem. The perfect marble was in the quarry, 100 miles away. The granite for the obelisk lay in a distant desert. The ambition was in the city square. Bridging that gap between source and site was the greatest engineering puzzle of the ancient world. It forced the creation of systems that were themselves marvels, a hidden network of extraction and transport without which the temples would have remained mere drawings in the sand. To understand the pyramid, you must first understand the profound hunger that built it. This hunger for stone created a new kind of currency. In the ancient world, the most valuable real estate was not always a palace or a fertile valley. It was often a scar on a mountainside, a place where the earth itself was broken open. A quarry was not merely a hole in the ground. It was a strategic asset as vital as a gold mine or a garrison. Because the stone you chose was never an accident, it was a statement carved in geology. Limestone was the workhorse, the dense, reliable flesh of a pyramid's core. Granite, hauled from the distant southern deserts of Egypt, was the empire's spine, reserved for the towering obelisks that pierced the sky and the sarcophagi meant to last for eternity. And marble was something else entirely. When the Greeks or Romans sheathed a temple in gleaming white marble, they were not just building, they were performing alchemy. They were transforming a mountain into light, into a symbol of purity, order, and divine favor that could be seen for miles. This made quarries the most guarded of state secrets. Controlling the source of the Parthenon's Pentelic marble meant controlling the very image of Athenian power. Owning the travertine pits near Rome meant you dictated the visual language of the empire's heart. These were not just mining operations, they were the birthplaces of imperial identity. Consequently, they attracted massive investment. You see the evolution of tools, from simple copper chisels to iron picks that could bite deeper into the rock. You see the emergence of sophisticated techniques for splitting colossal blocks along natural fault lines using nothing but wooden wedges and water. And most importantly, you see the rise of a permanent, specialized workforce. In Egypt, they were the Sariu, a community of quarrymen. In Greece, the Metallurgoi. These were not temporary laborers, but skilled artisans and engineers who lived in entire towns built around the quarry face. Their lives were dictated by the rhythm of extraction, their knowledge passed down through generations. They understood the stone's personality, its grain, its hidden weaknesses. The quarry town was a microcosm of the civilization it served, a dedicated engine whose sole purpose was to feed the endless architectural hunger of cities far away. So when you look at a polished marble column, you are not just looking at a beautiful rock. You are looking at the endpoint of a vast, state-controlled system, a testament to where political ambition met the bones of the earth and decided to make them speak. But a statement carved in stone is meaningless if it cannot reach the city square. This is where ambition met logistics and where our story finds its first great network. Look to the sun-baked cliffs of Aswan in southern Egypt. This was not just a quarry, it was a factory for the gods. Here, workers sought the iconic rose granite, a stone so hard it symbolized eternity itself. Extracting it required a deep conversation with the rock. They would locate natural fissures in the bedrock, then drill a line of holes and hammer in simple wooden wedges. The real ingenuity came next. They would soak these wedges with water. The wood would swell slowly, inexorably, with a force so patient and immense it could coax a 500-ton obelisk from the living mountain. This was engineering as a form of persuasion, yet the true marvel was not the extraction, but the journey that followed. The instant that obelisk was free, the clock started. It had to move, and for that, the ancients had a secret weapon more powerful than any machine, a highway built by nature. The Nile River was the indispensable lifeline, a liquid conveyor belt running the entire length of the civilization. Workers would drag these multi-ton monoliths on massive wooden sledges to the riverbank, a task often timed for the annual inundation when the floodwaters softened the earth and raised the river's edge. Then came the barges. We are not talking about simple boats. These were gargantuan, specially built vessels, floating platforms designed to cradle a weight that could sink an island. Once loaded, the Nile itself took over. Its predictable current flowed north, carrying these stone giants downstream with an efficiency no army of laborers could ever match. A journey of hundreds of miles overland would have been a generational undertaking. On the river, it became a matter of weeks. The obelisk quarried at Aswan would float serenely past villages and temples, a mountain on the move, until it arrived at its destination, perhaps the great temple complex at Karnak. This riverine system transformed a local geological resource into a national asset. It turned stone into a liquid, flowing north to fuel the dreams of pharaohs. But what happened when the stone reached its destination and the real work of ascent began? Yet the river's journey was only half the story. To reach that liquid highway, the stone first had to conquer the land. This was the true proving ground where ambition was measured in inches and sweat. Picture a single granite block destined for the Great Pyramid, a mass weighing 700 tons. That is the equivalent of 200 full-grown elephants. Moving such an object today would require a fleet of specialized trucks and a reinforced road system. The ancient Egyptians had none of that. Their solution was a masterpiece of applied physics and raw, coordinated human effort. They began by constructing a colossal wooden sledge, a platform designed to cradle the stone's immense weight. Beneath this sledge, they likely placed a series of wooden rollers, essentially felled tree trunks that acted as a continuous, moving track. This simple innovation transformed sliding friction into the far easier rolling friction, a fundamental leap in efficiency. But even with rollers, the force required was staggering. This is where the true logistical genius emerged. Teams of laborers, perhaps numbering in the hundreds, would attach ropes to the sledge. Their pulling was not a chaotic heave, but a precisely coordinated effort. Overseers likely used rhythmic drums or chants to synchronize the movement, turning a crowd into a single, powerful machine. Every muscle pull had to happen in unison to overcome the stone's inertia, and to make the path even smoother, they prepared the way. Archaeological evidence suggests they poured water or a slurry of wet clay on the causeway ahead of the sledge. This acted as a lubricant, further reducing the grinding resistance between the wooden rollers and the earthen path. For the most stubborn inclines or precise positioning, they might employ a system of levers and counterweights, using wooden beams as giant pry bars to nudge the block forward an agonizing inch at a time. The journey from the quarry face to the riverbank, a distance we might walk in minutes, could take weeks or even months for a single block. This phase was a symphony of mundane yet critical details. It required planning routes that avoided soft ground or steep slopes. It demanded a rotating schedule of work crews, with fresh teams replacing exhausted ones in a continuous cycle. It necessitated a parallel supply chain just to sustain the army of workers, providing food, water, and shelter in the barren landscape between the quarry and the Nile. This was not brute force, it was a highly refined form of project management. It displayed an understanding of materials, physics, and human organization that we often assume belongs solely to our modern era. The sledge, the rollers, the chants, the lubricated path, each was a cog in a vast machine made of people and purpose. They were turning impossible weight into deliberate, measurable motion. But once this terrestrial trial was complete and the stone was safely loaded onto its waiting barge, a new challenge emerged. The river highway was not without its own perils, and navigating a floating mountain required a different kind of courage and skill. The river was a gift, but not every civilization was so fortunate. Across the Mediterranean, the builders of classical Athens faced a different kind of challenge. Their ambition was carved not from granite, but from a luminous, almost ethereal stone, the brilliant white marble of Mount Pentelic. This was the stone of the Parthenon, a material that seemed to capture and hold sunlight, transforming solid rock into a vision of divine order and human reason. To clothe their acropolis in this radiant armor, the Athenians could not rely on a convenient, flowing highway like the Nile. Their geography demanded a more complex, hybrid solution, a testament to human ingenuity over natural advantage. The journey began high on the mountain slopes, in quarries that operated for centuries. Here, teams of skilled workers used iron tools to carefully extract massive rectangular blocks, following the natural grain of the stone. Each block was a potential column, a section of frieze, a piece of the city's soul. But the mountain was landlocked. To reach the building site atop the Acropolis, over 12 miles away, the marble had to first descend. The Athenians engineered a sophisticated overland network for this purpose. They constructed specially reinforced roads, paved with stone to bear the incredible weight. The blocks were loaded onto massive, rugged carts, their solid wooden wheels turning slowly under the strain. Teams of oxen, patient and powerful, provided the motive force, inching these crystalline burdens down from the heights. This arduous land journey ended at the bustling port of Piraeus. Here, the stone transitioned from land to sea. Using cranes and ramps, workers transferred the blocks onto sturdy coastal vessels, shallow drafted boats designed for the short but crucial voyage along the Attic coast. The sea leg, while brief, was vital. It bypassed the difficult terrain around Athens itself and delivered the marble to a point where the final, most dramatic ascent could begin. This two-stage system, a seamless integration of paved road, ox cart, and coastal barge, highlights a critical adaptation. Without a great river, the Athenians built their own logistical chain, piece by piece. The stone itself became a symbol. Pentelic marble was not just a building material, it was a cultural signature. Its luminous quality, its fine grain that allowed for breathtakingly precise carving, made it the perfect medium for expressing the ideals of Athenian democracy, philosophy, and artistic mastery. Every fluted column that rose on the Acropolis was a double statement. It spoke of beauty and balance, but also of immense practical capability. The very journey of the marble, from the hidden quarry to the most visible temple in the city, was a physical manifestation of the polis's collective will. It proved that a society could marshal resources, coordinate labor, and solve complex engineering puzzles not at the command of a single god-king, but through the organized ambition of its citizenry. The stone's path traced the outline of a civilization's logistical mind, yet for all its brilliance, the Athenian system was essentially regional, a masterpiece of local supply. To see a network of truly imperial scale, one that stitched together an entire continent, we must look to an empire that turned logistics into an art form of domination. But the Athenian model, brilliant as it was, remained a local network. To witness the full, breathtaking scale of what ancient logistics could achieve, we must turn to the ultimate architects of empire, the Romans. They transformed the movement of stone from a regional necessity into a globalized industry, a physical expression of their dominion over the known world. The Roman system was not about using what was nearby, it was about commanding everything, everywhere. They conducted a geological survey of their entire empire, identifying and cataloging the most beautiful and distinctive stones like a general inventories weapons. From the sun-drenched hills of Tunisia came a deep yellow marble they called giallo-antico, ancient yellow. From the mountains of modern-day Turkey, they extracted a dramatic purple and white stone known as pavonazzetto, peacock marble. Egypt supplied the deep red porphyry, a stone so associated with imperial power that its use was later restricted by law. Each quarry province became a specialized organ in the body of the empire, sending its unique essence back to the heart. And these were not independent businesses, they were imperial property, administered by state officials called procurators. This was state capitalism in stone, ensuring a steady, controlled flow of luxury material to feed the endless construction projects in Rome itself. The genius lay in the integration. The Romans built the world's most advanced road network, not just for legions but for commerce. These stone-paved highways connected inland quarries directly to bustling ports. And then they had their secret weapon, a highway far greater than any road, the Mediterranean Sea. The Romans called it Mare Nostrum, our sea, and they meant it literally. This vast, predictable body of water became the central conveyor belt of their empire. To maximize efficiency, they processed the stone at the source. At the quarry, artisans would rough-cut the marble into blocks or simple column drums, removing up to 70% of the useless weight. This was the ancient equivalent of shipping flat-pack furniture instead of a fully assembled cabinet. These semi-finished stones were then loaded onto the holds of sturdy merchant ships, which sailed the protected sea lanes with a regularity that would impress a modern shipping company. All routes led to Rome, specifically to a district on the Tiber River known as the Marmorata, the Marble Wharf. This was the grand central station of stone, a sprawling industrial port where shiploads from Egypt, Greece, Tunisia, and Turkey would arrive. Here, in vast workshops, master craftsmen would perform the final, precise carving, turning the rough blocks into polished columns, intricate floor slabs, and delicate statues. This system created something previously unimaginable, a reliable, long-distance supply chain. A wealthy senator building a villa on the Palatine Hill could walk into a mason's yard in Rome and order a set of columns made from giallo-antico from Africa, or a fountain basin of purple pavonazzetto from Anatolia. He could specify it with confidence, knowing that the imperial machinery would deliver. The very walls of Rome became a geological map of its conquests, a literal embodiment of the phrase, "all roads lead to Rome." But this monumental flow of material required one final, crucial element to function, an innovation so humble it is often overlooked, yet it was the silent linchpin that held the entire enterprise together. The silent linchpin of this entire imperial machine was the simple principle of buoyancy. A stone that would crush any cart or sledge on land could become weightless, cradled by the gentle, immense pressure of water. Rivers and seas were the natural allies of the ancient engineer, not just as routes but as active participants in the work. On land, moving a 100-ton block meant battling friction, gravity, and the sheer inertia of mass. On water, that same block became a passenger. The river current did the pulling, the liquid highway bore the weight, and the friction against the hull was a tiny fraction of what it was against dirt. This single physical truth turned geography from an insurmountable obstacle into the most efficient component of the supply chain. Civilizations worldwide learned to listen to the water. The sophisticated cities of the Indus Valley, millennia before Rome, floated millions of standardized baked bricks down river to their urban centers. Centuries later, Chinese engineers would harness the power of their great rivers to move colossal timbers and quarried stone for projects like the Great Wall, using the current to do the work of 100,000 men. But the water journey itself was often the easy part. The true engineering challenge, the moment of maximum risk and ingenuity, happened at the bookends of the voyage, loading and unloading. You could not simply roll a 200-ton obelisk off a riverbank and hope it floated. This required specialized infrastructure, turning wild shorelines into industrial ports. Builders constructed sturdy stone quays that could withstand constant impact. They engineered massive earthen ramps that sloped gently into the water, allowing sledges to be pulled right up to a waiting barge at low tide. As the tide rose or the barge was deliberately flooded with ballast water, the vessel would sink down, the sledge would be positioned over it, and then the water would be pumped out. The rising barge would lift the stone from its cradle, a seamless transfer of weight from land to liquid. For heavier or more precise lifts, the Greeks and Romans employed a brilliant machine, the treadwheel crane. Imagine a giant wooden wheel like a hamster wheel for humans. Workers would walk inside it, their collective weight and motion turning the axle, which wound a sturdy rope attached to the stone. This human-powered gear system provided the mechanical advantage to hoist multi-ton blocks vertically from a ship's hold or lower them perfectly onto a waiting dock. These cranes, often powered by teams of donkeys or even slaves, were the forklifts of the ancient world, the critical interface where the river's gift was finally claimed by the land. So the river was never just a path. It was a moving platform, a dynamic piece of engineering that transformed the impossible into the manageable. It allowed a civilization to think bigger, to source materials from further away, to conceive of monuments that defied the logic of the landscape. The waterway turned the crushing weight of ambition into something that could float, turning a mountain into a passenger on a journey to immortality. Yet for all the power of rivers and imperial roads, these networks of stone required one final, invisible ingredient to function, something even more vital than water or wood, the fuel that made the entire machine move. The Roman system was not just an abstract network, it was the physical pulse of the empire, and its greatest test came with one of history's most ambitious construction projects. The Flavian amphitheater, the Colosseum, was more than an arena. It was a logistical symphony composed in stone and water. Its sheer scale demanded an unprecedented flow of materials, and the Romans engineered a supply chain of breathtaking precision to make it happen. While the massive internal core used local volcanic tuff and brick, the building's iconic, gleaming skin required something special, a durable and beautiful limestone known as travertine. The primary source for this stone lay in the quarries near Tivoli, a formidable 20 miles east of Rome. On the surface, this distance presented a monumental challenge. moving thousands of multi-ton blocks across rugged terrain. The Roman solution was to break the journey into two perfect phases, mastering both land and water. First, they constructed a dedicated highway, the Via Tiburtina, a reinforced road built specifically to bear the constant, crushing weight of stone-laden carts. Ox teams would haul the rough-cut travertine blocks along this engineered path, not all the way to Rome, but to a strategic point on the banks of the Anio River. This was the critical transfer node. Here, the blocks were loaded onto wide, flat-bottomed barges. The Anio, a tributary, carried them gently into the main flow of the Tiber River. Now the real magic happened. The Tiber's current took over, becoming a natural, effortless conveyor belt flowing directly through the heart of the city. These barges, each one a floating piece of the future Colosseum, would dock at a wharf constructed astonishingly close to the rising construction site itself. This seamless integration of a purpose-built road and a natural water highway created a continuous, high-volume pipeline of material. There were no stockpiles waiting for months, no bottlenecks at the city gates. Stone moved from quarry to barge to construction crane in a fluid, uninterrupted cycle. This logistical fluidity is the hidden reason behind one of the Colosseum's most staggering facts: its breathtaking speed of construction. From foundation to completion, the entire monumental structure was finished in just 8 years. That rapid timeline, still astonishing today, was not a miracle of brute force, but a direct result of a supply chain that worked like water itself, finding the path of least resistance and flowing without cease. The Colosseum, therefore, is a monument to more than games or imperial power. It is a permanent testament to Roman logistical genius, where the journey of the stone was as engineered as the arches it formed. Yet even this perfectly tuned machine of roads and rivers relied on a deeper, more human foundation, the silent army whose labor powered every link in the chain. That logistical fluidity was built on a bedrock of human lives. To understand the true cost of a building boom, we must look past the monuments and into the quarry towns themselves. These were not temporary camps but permanent, pulsing settlements carved into the landscape they were consuming. A thriving quarry was a micro-city, a society of stone. You would find rows of barracks for the laborers, sturdy workshops where tools were forged and repaired, administrative offices bustling with scribes tallying output, and even temples where workers prayed to deities of the earth and for protection. This was a complete world, isolated and self-sufficient, dedicated to a single, monumental purpose. The people who lived here formed a distinct social class, the unsung architects of antiquity. Their lives were defined by the rock. In Egypt, quarrying was often a state operation with the gravity of a military campaign. Expeditions to remote sites like the Wadi Hammamat would include not just skilled stone cutters, but soldiers for protection, scribes to record progress, and support staff like cooks and water bearers. It was a mobile, disciplined society on the march, its survival as precarious as its mission was vital. In the Roman Empire, the hierarchy was more formalized, and skill could be a path to advancement. The Lapicidini, the master stone cutters, were highly valued artisans. Their expertise in reading the grain of marble, in executing perfect cuts for columns or intricate sculptures, was irreplaceable. For their service, some could even earn the ultimate reward, Roman citizenship, a testament to how critically the empire viewed this specialized knowledge. Yet alongside these skilled professionals, many quarries also relied on the labor of enslaved individuals or convicts, a reminder of the complex and often difficult human foundations upon which imperial glory was built. What sustained these communities across generations was not just organization, but a deep, accumulated wisdom. This was a craft passed from father to son, from master to apprentice. It was the intuitive knowledge of which vein in the cliff face held the finest, most flawless stone. It was the practiced eye that could spot a hidden fault line before it ruined a months-long effort. It was the muscle memory for the exact angle to strike a wedge to split a 200-ton block cleanly. This was the true human infrastructure, a living library of techniques that no papyrus scroll could fully capture. The sustainability of an empire's building ambition therefore hinged on a delicate balance. It required engineering marvels of transport, yes, but just as crucially, it depended on maintaining this human engine. Authorities had to keep thousands of workers fed in barren locations, sheltered from the elements, and motivated or compelled to return to the relentless work day after day. A failed supply convoy, an outbreak of illness, or a collapse in morale could halt the flow of stone as effectively as a dried-up river. The quarry town was the vulnerable, beating heart of the entire enterprise. When we admire a perfectly proportioned Roman column, we are seeing more than stone. We are seeing the end point of a vast social system, the quiet triumph of communities whose names history forgot, but whose hands literally shaped the world. The relentless rhythm of the quarry demanded constant innovation. To feed the ever-growing hunger for stone, ancient engineers had to become alchemists, transforming raw elements into tools that could persuade mountains to yield. Their first ally was not metal but fire. The technique known as fire setting was as simple as it was brutal. Workers would build roaring fires directly against the rock face, heating the stone to a searing temperature. Then, with a sudden hiss, they would douse the flames with water or vinegar. This rapid cooling caused a violent thermal shock, exploiting the different expansion rates of minerals within the rock to create a network of cracks and fractures. It was a method of controlled violence, using the fundamental physics of heat and cold to do the work that human muscle could not. Following this, teams could then use stone or bronze tools to pry loose the weakened blocks. In Egypt, for the impossibly hard granite, they employed even harder stones like dolerite. These dense, round pounders were used by workers in a relentless, percussive dance, literally pulverizing the granite grain by grain to shape obelisks and sarcophagi. It was a testament to patience, a conversation with stone conducted through millions of deliberate, echoing blows. But this was a slow, exhausting dialogue. The true revolution, the moment quarrying shifted from persuasion to precision, arrived with the ring of iron. Iron tools changed the conversation with stone forever. A sharp iron chisel could bite into granite where bronze would only blunt. An iron wedge, driven into a carefully drilled hole, could split a block with a clean, decisive crack instead of a slow, crumbling fracture. This was not just a stronger tool, it was a faster one. It dramatically increased the rate of extraction, allowing quarries to keep pace with the soaring demands of distant building sites. The efficiency of iron meant a single quarry face could feed multiple projects simultaneously, turning isolated operations into hubs of a networked economy. Yet this powerful new technology created a paradox. Iron tools were themselves products of a complex supply chain, requiring mines for ore, forests for charcoal, and skilled smiths to forge them. To feed the hunger for stone, civilization first had to master the hunger for metal. The quarry, therefore, became a nexus where two vast industrial systems met, the system of extraction and the system of tool-making, each dependent on the other. This interdependence highlights a profound truth about ancient logistics. It was never a single line from point A to point B. It was a web, a living ecosystem of resources and knowledge. The perfection of the quarrying tool was the first critical step, but it was meaningless unless the stone could then begin its journey. And that journey, across the deceptive calm of water, required a different kind of mastery altogether. The river was a highway, but it was not a tame one. Placing a 200-ton obelisk on a barge did not guarantee a smooth trip to the temple. This phase demanded a deep, intimate partnership with nature itself, a fluency in the language of water and wind. The captains who commanded these stone-laden vessels were not just sailors. They were hydrologists and meteorologists reading a world without instruments. Their most vital tool was the calendar, the rhythmic pulse of the seasons. For the Egyptians, everything revolved around the Nile's annual inundation. This was not a disaster but a scheduled event, a natural lifting of the world. As the floodwaters swelled, they raised the river's level, submerging sandbanks and deepening channels that were impassable for most of the year. This was the window. This was when the colossal barges carrying their mountainous cargo could glide from quarry to construction site with a foot of precious water to spare. Missing this seasonal tide meant waiting another full year, a delay that could stall an entire pharaoh's building program. So the movement of stone was choreographed to this celestial and earthly rhythm, a dance where human ambition moved in time with the river's heartbeat. On the open Mediterranean, the rhythms were different but no less critical. Roman and Greek shippers avoided the treacherous storms of winter almost entirely. Their sailing season was confined to the safer, predictable months from late spring through early autumn. Even then, they rarely ventured into the deep, open sea if they could help it. The standard practice was cabotage, sailing from headland to headland, always keeping the comforting line of the coast in sight. This was navigation by landmark, a slow but supremely reliable method. A captain would know that a particular stretch of white cliffs meant he was 2 days from a certain port, or that the water turned a specific shade of blue over a sandy shelf. At night, they steered by the fixed stars, following the same celestial pathways that guided Odysseus. The tools were simple, observation and memory, but the knowledge was profound and passed down through generations of seafaring families. This cautious, seasonal pattern imposed its own logic on the supply chain. All major stone shipments for projects in Rome or Athens had to be planned years in advance, with blocks quarried and rough cut in the off-season, ready to sail the moment the fair weather returned. The sea did not wait, and neither could the empire's architects, and the journey was not a simple one-way trip. This is a layer of logistics we often forget. Think of the empty barge. After delivering its monumental block to Thebes or Rome, the vessel had to return to the quarry to collect another. Going downstream with the current was a gift of nature. Going back upstream was a battle against it. For the return journey, there were no favorable winds in a river valley. The solution was human and animal power, applied with relentless patience. Teams of men, or sometimes oxen, would walk along specially maintained tow paths on the riverbank, hauling the empty barge against the current with long, thick ropes. This process, called warping or tracking, was slow, grueling, and essential. It meant that for every efficient, gravity-assisted float downstream, there was a laborious upstream crawl. The true cost of moving a stone included this return leg, doubling the human effort for every single block. This intricate dance with nature's rhythms, the flood cycle, the sailing season, the upstream struggle, was the silent, critical layer of planning in every ancient supply chain. It was the acknowledgement that the environment was not a passive stage but an active participant. To move a mountain, you first had to learn to listen to the river and read the sky. Yet mastering the journey of stone created a new problem, one of accounting and control. How did a pharaoh in Memphis know that his obelisk had left Aswan, or a Roman emperor track a shipload of marble from across the sea? This required one final, brilliant innovation, the birth of an ancient tracking system that turned chaos into order. Even the most sophisticated river networks had their limits. For a challenge that dwarfed the scale of the pyramids, we must travel to the windswept plains of Baalbek in modern Lebanon. Here, within the ruins of the Roman-era Temple of Jupiter, rests an engineering mystery carved in impossible weight. The famous trilithon, a foundation of 3 colossal limestone blocks, each one a staggering 800 tons. To put that into perspective, each of these stones outweighs 2 fully loaded Boeing 747 jets. The quarry that birthed these giants sits less than a kilometer away, a short walk across a gentle valley and a slight rise. This proximity makes the achievement not simpler, but infinitely more perplexing. With no navigable river to serve as a liquid highway, Roman engineers faced the ultimate overland puzzle. They had to move mountains literally, using nothing but dirt, wood, rope, and human ingenuity on a scale that borders on mythology. The solution was a temporary landscape of sheer force. Archaeologists believe they first constructed a massive, reinforced causeway, a road built not for carts, but for the earth itself to bear a concentrated, unimaginable load. To provide traction, they likely employed a system of colossal capstans, giant rotating drums anchored deep into the ground. Teams of men or oxen would walk in circles, winding thick, tarred ropes that pulled the stone sledges forward an agonizing inch at a time. Some theories suggest they may have even fashioned temporary, enormous wooden wheels directly onto the stone blocks themselves, transforming each megalith into a crude, rolling cylinder. The coordination required was a symphony of brutal physics. Every pull had to be synchronized, every rope checked for strain, every section of the causeway inspected for weakness. A single snapped cable or a crumbling roadbed could mean catastrophe, wasting years of quarrying effort in an instant. This was not efficient logistics in the Roman imperial sense. It was something far more profound. The staggering investment of labor and time for just 3 foundation stones reveals a critical truth. For certain symbolic, foundational elements, the elements that literally and spiritually supported the entire temple, no cost was too great. No logistical hurdle was too high. Baalbek represents the absolute zenith of pre-industrial heavy haulage, a place where engineering transcended practicality and entered the realm of monumental statement. It was proof that willpower, when applied with enough organized intelligence, could make the solid earth itself yield to passage. That monumental investment at Baalbek created more than just a temple foundation. It kick-started an entire economy. The true impact of these ancient logistics networks extended far beyond the stone itself, radiating outward to transform the landscapes they passed through. Every major state construction project acted like a giant economic stimulus package, circulating wealth and creating specialized jobs in communities that never once touched a chisel. Consider the sheer volume of material required just to move the stone. A single sledge capable of carrying a 100-ton block was itself a masterpiece of carpentry, requiring seasoned timber, precise joinery, and teams of woodworkers. The demand for thousands of these sledges, along with the wooden rollers placed beneath them, created a booming industry for local forests and workshops. Similarly, the miles of thick, durable rope needed for hauling teams did not magically appear. It spurred entire villages into the business of rope making, processing hemp or papyrus fibers into cables strong enough to pull a mountain. The textile industry flourished to clothe the vast workforce, while blacksmiths worked overtime to forge and repair the endless stream of iron picks, chisels, and wedges that wore down against unyielding rock. This was a cascade of demand where the hunger for stone created a parallel hunger for wood, fiber, and metal, energizing craft economies that had previously served only local needs. Then there was the constant, pressing need to feed the machine itself, meaning the people who powered it. An army of quarrymen, haulers, and sailors cannot work on empty stomachs. Sustaining a remote operation of thousands required a reliable, large-scale supply of food and water. This demand pulled surrounding agricultural regions into the project's orbit. Farmers who once grew only for their village now had a guaranteed bulk buyer for their grain, lentils, and dates. Herders found a steady market for their livestock. This injection of state purchasing power encouraged increased production, better irrigation, and more efficient farming techniques, as the penalty for a failed harvest was no longer just local hunger, but the collapse of a national project. The logistics network created a reliable commercial pathway for this surplus, integrating rural food producers into a centralized economic system for the first time. The most visible economic transformations happened at the nodes of the network itself. A simple riverbank loading point used season after season would naturally attract services. A blacksmith would set up a forge to repair tools and sledges. An inn would be built to house barge captains and officials. Merchants would arrive to sell supplies to the work crews. Before long, that loading point would grow into a bustling way station and then a permanent market town. Ports like Rome's Marmorata were not just industrial docks, they were vibrant commercial hubs. Taverns, warehouses, brokerage offices, and workshops for secondary stone cutting all clustered around the wharves, employing a diverse population of stevedores, clerks, cooks, and craftsmen. The stone's journey created a ribbon of economic opportunity along its entire route. A farmer could sell his produce to the port town, a carpenter there could build crates for shipping, and his brother might find work on the barges. Wealth generated by the state's ambition did not sit in a royal treasury. It flowed through the hands of countless individuals, creating an interconnected regional economy that could thrive for generations, long after the last block was set in place. This is the hidden legacy of the ancient building boom. It did not just create silent, static monuments. It built lively, resilient economies, proving that the path of a single stone could chart the course of prosperity for an entire civilization. The economic web spun by these logistics networks was powered by a complex human engine. To understand how these systems truly functioned, we must look at the people within them, a picture far more layered than simple tales of slave armies. It is true that large-scale state projects, especially within the Roman Empire, relied on unfree labor. The most grueling, repetitive tasks, the endless pulling of ropes, the back-breaking work of loading barges, the extraction of stone under a relentless sun, often fell to enslaved individuals or to convicts serving sentences. This was the brute force layer of the operation, the raw horsepower that turned engineering plans into physical motion. Yet to see this as the whole story is to miss the sophisticated machinery of ancient industry. These monumental projects could not have succeeded on muscle alone. They required a hierarchy of skill, a division of labor that was as carefully engineered as the transport routes themselves. The true architects of the supply chain were the specialists, the master quarrymen who could read the veins in a marble cliff and know exactly where to cut. The engineer who calculated the angle of a ramp or the capacity of a barge. The skilled carpenter who built the colossal sledges and cranes. The captain who could navigate a river's shifting currents with a priceless obelisk in his hold. These were not disposable laborers. They were trained artisans, often free citizens or highly valued state employees who commanded respect and better conditions. Their knowledge was the irreplaceable guide, the intelligence directing the immense physical power beneath them. This structure reveals the operational logic of the ancient world. Efficiency demanded that expertise and mass manpower work in concert. One provided the direction, the other provided the thrust. It was a harsh system, certainly, built on profound social inequities, but it was also a structured and deliberate one. Recognizing this complexity does not soften the realities of the past, but it does allow us to see these achievements for what they were, not the product of mindless oppression, but of a highly organized, if brutally pragmatic, system of production that leveraged every level of its society to turn ambition into stone. The sheer scale of this ambition is written not only in the monuments that remain, but in the very skin of the earth itself. For every column that rose in a city center, a corresponding wound was opened in a distant landscape. The ancient building boom was one of humanity's first large-scale acts of environmental modification, permanently altering the planet to feed its hunger for stone. Quarries like Carrara in Italy, still active today, are not natural features. They are anthropogenic landscapes, vast, terraced bowls carved by centuries of human effort, where entire mountainsides were systematically consumed. In the remote Egyptian desert, the site of Mons Claudianus stands as a ghost town of imperial industry, a sprawling complex of quarry pits, worker barracks, and broken pottery surrounded by a stark, excavated terrain. The removal of millions upon millions of tons of stone did more than just create a hole. It changed the local hydrology, diverting ancient water tables and drainage patterns. It scraped away topsoil and habitats, reshaping the ecology of entire regions for millennia. The impact radiated outward from the quarry face along every mile of the transport route. To move those mountains, you first had to build a road through the forest. The demand for wooden sledges, rollers, and the massive barges themselves required staggering amounts of timber, leading to widespread deforestation along river valleys and coastlines. In some cases, the landscape was engineered even more directly. To improve the efficiency of their liquid highways, Roman engineers would straighten tricky bends in rivers or dig auxiliary canals, physically rerouting water to serve the relentless flow of stone. This was terraforming on a practical scale, a deliberate reshaping of the natural world to optimize it for a single purpose: supply. Yet within this story of extraction, we also find intriguing hints of an early environmental consciousness, or at least a pragmatic understanding of sustainability. Some Roman quarries were worked in carefully planned, stepped benches. This wasn't just for the safety of the workers, it was a method to control erosion and manage the stability of the vast pits they were creating. And a depleted quarry was not always just abandoned. There is evidence that some played second acts in the community. A worked-out limestone pit filled with water might become a reservoir or a fish pond. Others became informal landfills, or their sheltered faces were later used for burials or even as the foundations for new buildings. These acts of repurposing show a complex relationship with the altered land, a recognition that the scar itself had become part of the human landscape. The environmental footprint of these ancient projects is a profound testament to their physical scale. It reveals a truth we often associate only with our modern industrial age, that a civilization's greatest achievements are always shadowed by the weight of the resources required to build them. The quarries and transport routes are the silent, enduring partners to the Parthenon and the Colosseum, reminding us that long before the age of factories and fossil fuels, humanity had already learned how to move mountains, and in doing so, had begun to leave a permanent mark on the face of the world. The flawless monuments that survive are the lucky ones. For every obelisk that pierced the sky, there were countless stones that never completed their journey. These logistical failures, frozen in time, are perhaps our most honest teachers. They reveal the immense pressures and razor-thin margins for error in a system that balanced colossal weight against fragile human plans. In the sun-scorched quarries of Aswan, the most famous failure of all still lies attached to the living bedrock. The unfinished obelisk is a monument to ambition overreaching technique. Cracked along a hidden fault line during its extraction, this 1,000-ton giant was abandoned where it was born. It is a ghost of a project, a stark lesson in the unforgiving physics of stone. The crack was not a small flaw, it was a catastrophic one, proving that even the most skilled quarrymen reading the granite's soul could be betrayed by a secret weakness. The decision to abandon it after an incalculable investment of labor speaks volumes. It was a cold, pragmatic calculation that even the gods of Egypt had to accept. The stone had spoken, and its word was final. The perils only multiplied once the stone took to the water. The Mediterranean seafloor is a museum of these logistical tragedies. Off the coast of Sicily, the wreck of the Marzami lies silent. This Roman merchant ship, dating from the 6th century, was not carrying raw blocks. Its cargo was a prefabricated church, a complete set of marble columns, bases, capitals, and even an altar, all precisely carved and ready for assembly at its destination. It was the pinnacle of efficient, long-distance supply. Then a storm hit. The ship, its hull groaning under the concentrated weight of so much stone, succumbed to the waves. That entire building, a prayer in marble, now rests in the dark, a testament to how the very efficiency of the system concentrating immense value in a single vessel also concentrated its risk. Every voyage was a gamble against the weather, and the sea did not care for imperial timetables. Even on land, a single miscalculation could bring everything to a permanent halt. Look back to the plain of Baalbek, home of the impossible trilithon. Nearby rests another colossal block, known as the Stone of the Pregnant Woman. It is even larger than the foundation stones, estimated at nearly 1,000 tons. And it lies abandoned in its quarry, only partially separated from the bedrock. Why was this true behemoth, larger than any block ever successfully moved in antiquity, left behind? The most compelling theory is not a crack, but a simple logistical error. Perhaps the engineers realized too late that the route they had prepared from the quarry to the temple site could not support its unprecedented mass. The causeway may have been inadequate, or the grade of the slope too steep for their capstans and ropes to manage. It was a failure of planning, not of extraction. The block was simply too big to move with the technology at hand, a permanent monument to the outer limits of ancient engineering. These frozen failures are not signs of incompetence. They are the boundary stones of the possible. They highlight that every completed column, every raised obelisk, represents a victory over 1,000 potential disasters. Each one survived the gamble of the quarry, the mercy of the river, the fury of the sea, and the precision of the hauling crew. The chain was long, and every link was fragile. When we admire the wonders of the ancient world, we are not just looking at success. We are looking at the narrow path of triumph through a wilderness of potential ruin. The stone's journey was never just about physics or economics. For the most sacred objects, the logistical route became a spiritual pathway, a ritual in motion. In ancient Egypt, the transport of an obelisk was a cosmic event. This towering needle of granite was far more than architectural ornament. It was a frozen ray of sunlight, a physical connection between the pharaoh and the sun god Ra. Therefore, its journey from the dark womb of the Aswan quarry to its raised position at a temple gateway was carefully staged as a divine drama. It reenacted Ra's own daily voyage across the sky. As the colossal barge bearing the obelisk floated north with the Nile's current, it was accompanied by a flotilla of priests and officials. Ceremonies were performed at key points along the riverbank, purifying the route and inviting the gods to witness this moving mountain of light. The final haul from the river to the temple, that agonizing overland pull, was transformed into a sacred procession. Crowds would gather, not just to gawk at the engineering, but to participate in a living myth. The slow, deliberate advance of the stone was the sun's own progress, and the pharaoh overseeing it was demonstrating his role as the god's representative on earth, literally pulling the divine into the heart of his kingdom. The logistical nightmare was thus wrapped in a layer of profound meaning, turning every strain of the rope into an act of worship. This symbolic layer was a powerful tool of statecraft. It transformed back-breaking labor into a privileged participation in something eternal. A worker pulling on a sacred rope was not just a laborer, he was an essential actor in a ritual that sustained the cosmos. This ideological framing helped motivate the immense, coordinated effort required, blending practical necessity with spiritual purpose. We see similar transformations across cultures. For the Maya, the transportation of a carved stone stela, a monument recording royal deeds and divine ancestry, was itself a ceremonial event. The stela was not an inert slab, it was a captured piece of history and identity. Moving it from the workshop to the central plaza involved ritual processions with chanting, incense, and offerings. The act of raising it vertically was a moment of rebirth, as the stone and the history it bore were planted into the living world of the community. In this way, the movement itself became a performance of legitimacy. The public spectacle of the stone's journey reinforced the message carved upon it, that the ruler had the divine authority and organizational power to command both the earth and the people. The logistical operation thus served a dual master. It solved a physical problem of weight and distance, while simultaneously broadcasting an ideological solution to questions of power and belief. The stone ceased to be mere material. From the moment it was chosen, it was a consecrated object, a passenger on a pilgrimage. Its path from quarry to site was a rite of passage, a transformation from raw potential to eternal fixture. The ceremonies along the way were like stations of the cross, each one marking a step closer to its destined purpose. When it finally settled into its prepared socket, the journey's end was not just a construction milestone, it was a spiritual homecoming. The silent, immobile monument we see today is the final frame of a long and sacred story, a story written in sweat, ceremony, and deliberate, majestic motion. This deep fusion of logistics and belief reveals the true ambition of these projects. They were not merely building structures, they were orchestrating realities, weaving together the physical, economic, and divine threads of a civilization into a single, unbreakable tapestry. The fusion of logistics and belief was not a singular invention, but a human response to a universal, physical challenge. The same fundamental problem, how to move the immovable, echoed across continents, sparking astonishingly clever, yet completely independent solutions. Far from the Mediterranean, in the breathtaking heights of the Andes, the Inca Empire faced a logistical puzzle that makes even Baalbek seem straightforward. Their signature architectural style, seen at breathtaking sites like Sacsayhuaman above Cuzco, features colossal, irregularly shaped stone blocks fitted together with a precision that defies a razor blade. But how did they move these multi-ton giants, some weighing over 100 tons, across the rugged spine of the Andes? They had no wheels suitable for the terrain, no strong draft animals like oxen, and no navigable rivers running to their mountaintop citadels. Their solution was a masterpiece of human adaptation. They built an empire along a network of royal roads, thousands of miles of paved and graded pathways that traversed some of the most dramatic geography on Earth. Along these roads, movement was powered by the most abundant resource available, people. Enormous work crews, organized through a labor tax system called the mitre, would transport the stones using a combination of earthen ramps, ropes made from tough grasses, and wooden levers. The most likely method involved dragging the blocks on rollers or simply sliding them along prepared causeways lubricated with clay. The coordination required was immense, with teams relaying the stone from one district to the next in a carefully orchestrated chain of human power. This system was perfectly adapted to its environment, turning the strength of a highly organized society into the primary engine for moving mountains, proving that a river of people could be as effective as a river of water. Meanwhile, on the other side of the world, ancient Chinese engineers approached the same problem from the opposite direction. They did not conquer mountains by avoiding rivers, they mastered the rivers themselves. For monumental projects like the Grand Canal, the Great Wall, and the vast imperial tombs, the Chinese developed an unparalleled sophistication in water management for transport. They did not just use rivers, they redesigned them. They constructed complex networks of canals, building locks and dams to control water levels with precision. This allowed them to move colossal timbers and quarried stone across vast distances through an engineered landscape, creating a predictable, man-made liquid highway. A barge carrying stone for an emperor's tomb could be raised or lowered through a series of locks to traverse changing elevations, a technology that would not appear in the West for centuries. This system minimized the brutal overland haul, leveraging the gentle, sustained force of buoyant water to do the work of 1,000,000 porters. The Chinese approach reflected a deep philosophical and practical harmony with water, viewing it not as an obstacle, but as the most malleable and powerful tool in the builder's arsenal. These parallel stories, from the peaks of Peru to the plains of China, reveal a profound truth. The core challenge of mass and distance acted like a kind of intellectual catalyst, pressing separate civilizations toward similar principles despite their complete isolation. They all discovered that to move great weight, you must outsmart friction. The Inca used ramps and lubricated paths. The Chinese used water to make friction nearly vanish. They all learned to leverage natural pathways, whether it was the Inca following the natural ridges connected by their roads, or the Chinese following and then reshaping the flow of their great rivers. This was not a technology that spread, but a logic that emerged independently, a testament to the shared ingenuity of the human mind when confronted with a truly monumental task. The solutions looked different, one a symphony of coordinated muscle on stone roads, the other a ballet of hydraulics on artificial waterways, but the underlying score is the same. It is the story of turning landscape from a barrier into a partner, and of transforming a society's collective will into a force that can redirect the very weight of the earth. The quest for stone did more than move mountains, it etched permanent pathways into the earth itself. While we often picture Roman legions marching on those iconic paved roads, the very stones beneath their feet tell a deeper story. The relentless need to move quarried material from source to river and from port to building site demanded something more reliable than dirt tracks that turned to mud. It demanded all-weather highways, roads that could bear the crushing, constant weight of laden carts without crumbling. This economic imperative became one of the greatest drivers of Roman engineering. A road like the famed Via Appia was not merely a military corridor, it was an industrial supply line. Its sturdy surface, often paved with the very basalt blocks quarried from nearby volcanoes, allowed ox teams to haul stone year-round, turning seasonal, weather-dependent projects into continuous, unstoppable campaigns of construction. The road itself was both the means and the message, a physical declaration that the flow of resources would not be interrupted. This created a powerful, self-reinforcing cycle. Better roads meant more efficient logistics, which allowed for even grander and faster building projects. The success of those projects, in turn, justified the immense investment in paving another road, extending the network further. Infrastructure built for one specific purpose, to feed the hunger of a building boom, became the unexpected backbone for everything else. These stone rivers of transport soon carried far more than marble and travertine. They carried grain from Egypt, olive oil from Spain, and spices from the East. They carried the imperial post, the tax collector, and the ideas of philosophers. A road originally engineered to connect a quarry to the Tiber became a vital artery for trade, administration, and cultural exchange. The legacy of the quarryman's struggle, therefore, is written in the enduring grid of stone that stitched an empire together. Long after the temples and amphitheaters were completed, this network remained, facilitating control and communication for centuries. It is a profound reminder that the solutions to our most immediate physical problems can sometimes lay the foundation for civilizations yet to come. These intricate networks were not left on any ancient map. So how do we know the story of a single stone's journey from a distant quarry to a finished monument? The answer lies with modern archaeological detectives who piece together clues from a startlingly diverse array of sources, slowly mapping the invisible. The first clues are often written in the stone itself, inscriptions chiseled directly onto unfinished blocks or quarry walls act as ancient packing slips. A note in a Roman quarry might record the names of the work crew, the date of extraction, and even the destination, like a tag reading, "For the Temple of Jupiter." In Egypt, hieroglyphic markings on pyramid blocks sometimes name the work gang, such as the Friends of Khufu team, offering a rare personal glimpse into the human organization behind the mass. When a block reached its destination, its geological fingerprint could be matched back to its source. Modern geologists use thin section analysis, examining a sliver of stone under a microscope to identify its unique mineral composition, effectively proving that a column in Rome was born in a specific mountain in Turkey. The most dramatic evidence often comes from catastrophic failure. Shipwrecks resting on the Mediterranean seabed are frozen moments of transit, time capsules of logistics interrupted. The wreck we mentioned earlier, carrying the prefabricated marble church, is a perfect example. Its cargo was not raw material, but a finished product in mid-shipment, revealing the advanced just-in-time delivery system of the late Roman Empire. By studying the layout of the stones in the hold, archaeologists can deduce how they were loaded for stability, what the ship's route likely was, and even estimate the sailing season of its final, fatal voyage. On land, the evidence is more subtle but equally telling. The ground itself holds memories. Near ancient quarries, you can sometimes find deeply worn tracks in the bedrock, parallel grooves polished smooth by the passage of countless wooden sledges carrying their immense burdens. These are the scars of the supply chain, a permanent record of the path every block took to begin its journey. When physical evidence is sparse, archaeologists turn to experiment. This is the field of experimental archaeology, where theories are tested with physical action. Teams have attempted to move multi-ton stones using only the materials and methods presumed to be available to the ancients. They build wooden sledges, pour water as a lubricant, and coordinate crews of volunteers pulling on ropes. These experiments are not stunts, they are rigorous scientific inquiries. They answer practical questions. How many people does it really take to move a 5-ton block on rollers? How effective is a lubricated clay slipway? Does a team pulling in rhythm actually generate more force? The results turn abstract ideas about possible into concrete data on probable, grounding our understanding in the reality of physics and human endurance. Meanwhile, technology from the skies offers a god's eye view. Satellite imagery and LiDAR, which uses lasers to map terrain through forest canopy, can reveal the faint outlines of lost roads leading from forgotten quarries, or the geometric shapes of loading docks along silted-up riverbanks, stitching together fragments of the landscape-scale network. Finally, the smallest marks tell a grand story. The tool marks left on an unfinished obelisk or a partially carved column are like a craftsman's signature. The spacing and angle of chisel strikes can indicate the type of tool used, whether it was copper or iron, and even the technique of the worker. A series of drilled holes in a straight line suggests the use of wooden wedges for splitting. A smooth, polished surface might indicate the final stage of abrasion with sand and water. By reading these microscopic histories, experts can reconstruct the entire chain of production, from the first blow that freed the stone from the earth to the final touch that prepared it for its sacred role. This multidisciplinary puzzle-solving, blending geology, epigraphy, maritime archaeology, and hands-on experiment, is how speculation slowly solidifies into documented history. It allows us to trace the ghostly outlines of the systems that were the true lifeblood of ancient ambition, proving that the story of these civilizations is written not only in their glorious endpoints, but in the very paths their stones traveled to get there. These silent tool marks and worn tracks are no longer just static clues. Today, they are the raw data for a digital revolution in understanding. By feeding this archaeological evidence into powerful computer models, researchers can now run simulations of the ancient world, testing theories of logistics with a precision our ancestors could never have imagined. This is the frontier of digital archaeology, where the past meets the processing power of the present. Using Geographic Information Systems, or GIS, experts can create layered maps of the ancient landscape. They input the exact location of a quarry, the known destination, and then layer in every variable the original engineers faced. The software analyzes the slope of the terrain between points, identifying every hill and valley. It maps the known locations of ancient rivers, streams, and seasonal water sources crucial for both hauling crews and for floating barges. It overlays the remnants of old road networks, some now invisible to the naked eye but detectable from aerial surveys. The computer then calculates not one but dozens of potential routes from source to site, each one graded for efficiency. It can tell us which path, while perhaps longer in distance, would have offered the gentlest grade for pulling a massive sledge, thereby saving weeks of labor and immense physical strain. This moves us from wondering how they might have done it to understanding the specific, optimal choices they likely made given their tools and their environment. Beyond mapping the route, computational modeling tackles the human equation. Researchers can input the known weight of a specific block, like one of the trilithon stones at Baalbek, along with data about the friction coefficient of a wooden sledge on a lubricated path. The model can then estimate with surprising accuracy how many individuals would be required to pull it, but it goes further. It can calculate the required force and from that deduce the staggering daily caloric intake needed to fuel that workforce. This transforms abstract admiration into a quantified reality. It shows us that moving that single block wasn't just about ropes and ramps. It was about a parallel, massive supply chain of grain, dates, and water just to keep the human engines running. This digital lens allows us to ask entirely new, profoundly practical questions. Was the chosen path the absolute best one, or were there political or sacred reasons for a slight detour? If a storm delayed a barge by 3 days, how did that ripple through the entire construction schedule? By applying modern engineering and nutritional science to these ancient problems, we gain a respect that is rooted in numbers, not just wonder. We begin to see the hidden intelligence in every decision, the accumulated wisdom that turned a seemingly impossible task into a repeatable, managed process. This digital reconstruction does more than illustrate history. It lets us stress test it, revealing the resilient genius embedded in operations that shaped our world. This invisible calculus of efficiency was the true architect of style. The moment a civilization mastered the movement of stone, its architectural vocabulary exploded. Consider the leap from Egypt's Old Kingdom to its Pyramid Age. For generations, royal tombs were modest structures of mud brick, limited by what could be hauled short distances by human hands. Then came the logistical breakthrough, the deep understanding of the Nile as a liquid highway. With the ability to float million-ton blocks of limestone from quarries hundreds of miles away, the very idea of what a tomb could be was shattered. The mudbrick mastaba was no longer the limit. Architects, now empowered by a supply chain that could deliver mountains, began to dream in impossible scales. The step pyramid of Djoser was a first, staggering experiment. Then, with transport systems refined to a predictable rhythm, the smooth-sided true pyramid became not just possible but inevitable. The pyramid shape itself is a monument to logistical confidence, a form that could only exist because the river could guarantee an endless, reliable flow of stone to the desert plateau. The architecture did not create the logistics created the architecture. Centuries later and a continent away, a similar revolution unfolded in color. Early Roman architecture was sturdy, practical, and locally sourced, built from the volcanic tuff and travertine found near the city. Then came the mastery of the Mediterranean sea lanes. Suddenly, the effective cost of a beautiful stone from across the sea plummeted. It was no longer a fantastically rare treasure, but a reliable commodity that could be ordered in bulk. This logistical triumph directly birthed the iconic polychrome style of Imperial Rome. Architects were no longer constrained by the gray and brown palette of local quarries. They could now compose in a symphony of hues, inlaying floors with brilliant yellow marble from Tunisia, sheathing walls in deep green from Greece, and setting columns of purple and white stone from Turkey. The entire aesthetic of imperial power, that dazzling, multi-colored display of wealth and reach, was made possible because the supply chain had become a seamless, predictable service. The widespread use of decorative imported marble wasn't just a fashion. It was the physical proof that the empire's logistical network was operating at peak efficiency. Every incremental advance in transport technology quietly expanded the boundaries of the possible. The development of larger, more stable barges meant a single voyage could deliver a column capital and its base together, ensuring a perfect match. The refinement of the treadwheel crane allowed for the precise placement of heavier, more slender columns, enabling the airy, spacious interiors of later Roman basilicas. Safer, more predictable sea lanes, mapped by generations of captains, meant architects could specify stones from 3 different provinces for a single project with confidence they would all arrive in the same building season. Each of these improvements lowered the friction, the risk, and the effective cost of ambitious design. The building boom, therefore, was never simply a period of more construction. It was a period of profound transformation in the language of built space itself. New materials available in new quantities gave rise to new forms, new aesthetics, and new statements. Logistics did not just deliver stone, it delivered possibility. It was the silent partner in the drafting room, whispering to the architect that yes, that soaring vault or that intricate, multicolored floor could indeed be built, because the invisible network was now robust enough to support the vision. The art was always waiting patiently for the system to catch up. But this magnificent machine was not immune to its own success. The very systems that fueled monumental growth could also become engines of exhaustion. Could these networks of stone and sweat last forever? The historical record whispers a sobering answer: no. For all their ingenuity, these were not self-sustaining natural cycles, but fragile, state-managed enterprises, and they sometimes collapsed under the immense weight they were built to bear. Consider the trajectory of Imperial Rome. The city's appetite for marble was literally insatiable, a demand that drove quarrying on an industrial scale across the Mediterranean. Over centuries, this relentless extraction began to deplete the most accessible, highest quality deposits. The beautiful giallo antico from Tunisia, the flawless white marble from Greece, these were finite resources. As the easy stone ran out, operations had to push deeper into mountainsides or further into remote, difficult terrain, increasing the cost and complexity of every single block. And the cost was already staggering. Maintaining the vast fleet of specialized barges, the legions of skilled and unskilled laborers, the engineers and administrators, and the fortified way stations along thousands of miles of routes required a river of gold flowing from the imperial treasury. This logistical marvel was a luxury of peak power, a symptom of overwhelming wealth and control. When that foundation began to crack, the entire edifice trembled. As the Roman Empire faced political instability, economic inflation, and external pressures in its later centuries, the state's ability to fund this non-essential, monumental infrastructure evaporated. Funding was diverted to armies and defense. The complex, just-in-time delivery system for marble began to stutter. The quarries, once buzzing with permanent communities, slowed their rhythm. The transport networks, lacking state funds for maintenance, started to decay. Barges were not repaired, roads were not cleared, and the specialized knowledge of crews began to disperse. The great building booms, which had defined Rome's visual identity for centuries, gradually ceased. The wharves of the Marmorata grew quieter. This pattern is not unique to Rome. We see echoes in other civilizations where the monumental scale of construction eventually outstripped the economic or environmental capacity to support it. The end of a building boom, therefore, is a diagnostic tool. It reveals as much about a society's underlying pressures as its beginning reveals about its strengths and ambitions. The silence of the quarry is often the first sign of a deeper fracture, a reminder that the journey of stone is a conversation between human will and the hard, practical limits of the world it inhabits. The silence of an ancient quarry is never truly empty, for the principles discovered there still echo in the hum of our modern world. Those first engineers, coaxing mountains down rivers, were mapping a logic that now underpins our entire global existence. Their solutions to moving the immovable became the timeless fundamentals of logistics, a playbook we follow even if we have forgotten its authors. Look at any modern port, a sprawling landscape of stacked metal containers. This is the direct descendant of the Roman Marmorata, a hub where goods from every corner of the earth converge before being dispatched. Our hub and spoke networks, with airports and distribution centers, are simply the same pattern written in steel and jet fuel instead of stone and water. The standardized shipping container is the perfect modern parallel to the Roman practice of rough-cutting marble at the quarry. Both are acts of brilliant simplification, transforming a chaotic assortment of goods into uniform, stackable, easily transferable units. A container from a factory in Vietnam and a semi-finished column from a Turkish hillside serve the same purpose. They maximize efficiency by minimizing handling and lost space, turning a complex journey into a predictable, repeatable process. This ancient logic reaches its peak in concepts like just-in-time delivery. When Roman barges arrived at the Tiber wharf with travertine for the Colosseum, the stone did not sit in a warehouse for months. It moved almost directly from ship to crane to rising wall, a continuous flow that allowed the amphitheater to be completed in a mere 8 years. Today, a car factory operates on the same precise rhythm, with parts arriving from suppliers not a moment too early or too late, synchronized to keep the assembly line moving without costly pauses or stockpiles. The core challenge is identical, coordinating a vast, dispersed network to deliver the right component to the exact point of need at the precise moment it is required. The stakes are just as high. A breakdown in that flow halts not a temple but an entire industrial plant. Even our most audacious modern constructions are conversations with these ancient problems. Building a skyscraper or a suspension bridge is not so different from raising a pyramid or a cathedral. The scale has changed, but the fundamental puzzle remains. How do you source, transport, and assemble massive, often custom-made components? A steel beam for a skyscraper is forged in one country, shipped across an ocean, and then lifted hundreds of feet into the air, a journey requiring coordination between miners, metallurgists, shippers, truckers, and crane operators. This is the same multi-stage, multidisciplinary symphony that moved an obelisk from Aswan to Thebes, just with different instruments. The solutions still hinge on optimizing the route, whether it is plotting the most fuel-efficient sea lane for a cargo ship or, millennia earlier, waiting for the Nile's flood to raise the water level for a barge. We still seek to standardize the cargo, whether in uniform container sizes or in prefabricated building modules. And above all, we must perfectly synchronize the workflow, aligning the schedules of thousands of people and machines across continents and time zones. By studying the ancient models, we gain a profound appreciation for the conceptual bones of our own world. Our global supply chains, for all their digital tracking and mechanized power, are built upon a foundation laid by quarrymen and barge captains. They discovered that moving great weight is less about raw force and more about reducing friction, both physical and organizational. They learned that the most powerful tool is not the lever or the rope, but the shared plan, the synchronized effort, the optimized path. When a modern logistics manager studies a map to shave a day off a shipping route, they are engaging in the same intellectual exercise as the Egyptian engineer timing his obelisk's journey to the seasonal flood. The context is new, but the calculus is ancient. This continuity reveals a humbling truth: our hyper-connected civilization, for all its technological marvels, still runs on a very old operating system, one written in the language of water, stone, and human coordination. That operating system was written in stone long before it was written in code. The silent rivers and forgotten quarry roads were the true architects of the ancient world's wonders. As we have journeyed from the Nile to the Tiber, from Aswan to the slopes of Pentelic, a clear picture emerges from the dust. These breathtaking building booms were not miracles of isolated genius, not the product of a single visionary mind. They were triumphs of systematic, large-scale organization, the culmination of thousands of invisible decisions made by engineers, captains, and foremen whose names are lost to time. This is a hidden history of innovation, but not just in tools. It is a history of innovation in management, in the coordination of labor across vast distances, and in the patient solving of problems that had never been faced before. Every polished column is a lesson in applied physics. Every raised obelisk is a masterclass in seasonal planning. Every mosaic of imported marble is a testament to an empire's ability to run a reliable, transcontinental delivery service. So the next time you stand before an ancient monument, or even see a photograph of one, try to see beyond the silent stone. See the incredible journey it undertook. See the quarrymen reading the rock's soul. See the crews chanting in unison as they heaved on ropes. See the barge captain squinting at the horizon, guiding a mountain across the sea. That journey speaks to something fundamental in us, to humanity's relentless collective drive to shape our world, to leave a mark no matter the obstacle. Let these stones remind you that behind every great achievement, every structure that seems to defy its era, lies an even greater system, a network of thought, effort, and connection. It is a powerful reminder that what we build is only ever as strong as the unseen pathways that bring it to life. If you found this deep dive into the hidden arteries of history fascinating, there are countless more mysteries to unravel. Subscribe to continue exploring the incredible systems of our past, and we would love to hear from you. Share in the comments below which ancient supply chain or logistical feat amazes you the most.